As I said before, that the stress intensity factor is a local measure of the intensity of the stress fields in front of a crack tip, which we get from an asymptotic analysis done at the tip of a sharp crack. Whereas G, the energy release rate, is a global measure. But in linear elasticity, they can be connected to each other, and this is how we do it. Now think of this thought experiment again, where I have a crack of length A, and this length delta A is what is going to be an extension of the crack, but not yet is. So at this point, when this delta A region is not a crack, has not become a crack yet, you have the stress field of this existing crack. So you have a stress intensity factor K1 at the crack tip, which is a function of the crack length divided by root 2 pi x1. And since the, let's say this is a mode 1 case, and since it's a mode 1 case, the angular function is 1 in along theta equal to 0. So this is the stress field. 1 by square root x1 is the stress field that you have on this region, which is going to become a crack. Now so this region, after it becomes a crack, is drawn here, and this length is delta A, and now we want to close it back to this situation. In order to close it back, we have to now apply whatever tractions were there on the upper surface. We have to apply it in the reverse direction. We have to apply these tractions in the reverse direction. So the tractions were high at the tip of the uh, tractions were high at the tip of the main crack, and lower as we go further away from the tip, and decreased as 1 by square root x1. So to close it down, we will have to apply these tractions, which are basically sigma 2 2 given by this quantity. And by how much do we have to close down? So we will have to close down by the opening of the crack once it has formed. So this opening is U2 plus on the upper face and U2 minus at the lower face, and these openings we can again calculate based on a crack of length A plus delta A. So this extended crack now has a stress intensity factor here, which is given by K1 A plus delta A, and the displacement field should be based on this stress intensity factor, whereas the stress field that you have to use to close it, the traction field that you have to use to close the crack, should be based on K1 A, which is the stress intensity factor of the main crack, and this is the stress intensity factor of the eventually extended crack. Okay, so to close it down, the delta U that you will have to satisfy is, again, in the previous problem, half of P times delta. So at every location dx1, you have a crack area of T times dx1, and you apply a sigma 2 2 on that. So sigma 2 2 times T dx1 is the small element of force df x1 that you are going to apply to close it down, and you will have to close it down by this displacement, which is u2 plus at the top and u2 minus at the bottom, and the directions are different. So this has to be closed down in the negative x2 direction. This has to be closed down in the positive x2 direction. So the total change in strain energy, change in strain energy of the small element would be sigma 22 times this multiplied by u2 plus minus u2 minus. Uh, this reflects the fact that the bottom and top faces, this minus reflects the fact that the bottom and top faces are moving in opposite directions. So this is the total strain energy when you integrate from 0 to delta A over this region. This is the total strain energy that will be expended to close uh, the new crack formed back to its original state, original closed state, as in this figure. So this energy has now got to be calculated. Sigma 22 comes from the fact that sigma 22 is the stress field ahead of the main crack. So sigma 22 is the stress field ahead of the main crack. So this is K1 with K1 as a function of A, and U2 plus and U2 minus for a mode 1 crack is given by K1 root pi uh, root 2 pi r divided by 4 pi mu kappa plus 1 at theta equal to 0. You can look back your displacement relations for a mode 1 crack. So, sorry, this is at theta equal to pi, theta equal to pi. So for the extended crack, this is your r direction, this is your r direction, this is your theta. So at theta equal to pi, at theta equal to pi, for a k1 given by a plus delta a, you have an opening that is now given by an r which is this. So at opening at this point, the r at this point is this, and this r, the magnitude of this r is delta a minus x1. So remember, x1 is measured from the main crack tip, so this is your x1. X1 measured from the main crack tip. This is delta A, the total is delta A, the crack extension, and delta A minus x1 is your R. Okay, so in place of R, I write delta A minus x1, and the total strain energy change is now calculated using this integral, with the assumption that for this small extension, K1 did not change much. So this is an important assumption here. We are dealing with a small extension delta A. So K1 did not change much. K1A plus delta A is equal to K1A. Given that, this is the integral that we now have to evaluate. So there's a dx1 missing here. So this is the integral that we now have to evaluate, and that's what we do. It's easy integral to evaluate. You can make the substitution, and the integral comes out to be pi delta a by 2, and use the increase in crack area delta a equal to T delta A, and so you have delta U equal to this, and then take the derivative of this with respect to delta A. You are left with, now kappa 1 you can use for plane stress and plane strain. There are different expressions. Also, you use the fact that mu is equal to E2 into 1 plus mu. So if you use that, this is mu. I'll correct it in the notes. So once you use that, you get this very useful relations that G is equal to K1 square by E for plane stress, and K1 square by E prime for plane strain, where E prime is E by 1 minus nu square. Remember here that this delta U, what we have calculated is delta U by delta A from this relation. What we have calculated is this, but this is the energy required to close the crack. To open the crack, this much of energy will be released. So this numerically will be equal to the energy released, because this is an elastic system, but you will have the minus sign, because while opening the crack, its energy released while closing the crack, it is energy that has to be supplied to the system. So this numerically will give you the G, and that numerical G would be K1 square by E for plane stress and K1 square by E prime for plane strain. This is for mode 1, and this is a very, very important relationship because it allows you to get the K for a crack, uh, mode 1 K for a crack, provided you have the G. So if you know the G, you can get the K. If you know the K, you can get the G. Now, K is a local measure, G is a global measure, and this is what connects it, provided everything is elastic. Provided everything is elastic, you have a one-to-one connection between the local measure of stress intensity and the global measure, which is the energy release rate. Now, this is only for mode 1. If you do it for other modes, then you can show that G is actually a combination of mode 1, mode 2, and mode 3 stress intensity factors. So the energy per unit area of crack extension is uh, given by this for mode 1 and mode 2 plus this for mode 3. So if you have a mixed mode situation where you have mode 1, 2, and 3 operating simultaneously, then your G will be a combination of the three modes of stress intensity factor. So given K1, K2, K3, you will be able to get G, but the other way is not possible. So given G, you will not be able to say right away what is K1, what is K2, what is K3, because G is a combination of all three. However, if you are sure about the mode of the crack, if you say, for example, know that K2, K3 does not exist, it's a pure mode 1 problem, then of course you have an handle on K1, K2, whatever the case may be. Let us do a few problems using the energy concept. So here is a film. The yellow part is a thin film on a rigid substrate, and this film is bonded to the substrate over all regions except uh, at this place where it is debonded, and it is being pulled by this tensile force F as shown. Now we need to find the stress intensity factor for this particular film at ahead of the debond. So stress intensity factor for the crack tip here. Now we start by uh, realizing that if I take a small element here, this small element is actually subjected to sigma 11 and sigma 33, nothing else. That is because here the normal is 0, 1, 0, and this is a traction free surface. So here sigma 2, 2, sigma 1, 2 are 0. This is also a traction free surface where sigma 2, 2, sigma 1, 2 are 0. This thin film is thin, so we can assume that sigma 1, 2, sigma 2, 2 are 0 all through the thickness of the film. So sigma 2, 2 is 0. Sigma 1, 1 is due to the force F that is applied, and sigma 3, 3 is because of the condition that this is a uh, plane strain case, and therefore epsilon 3, 3 is equal to 0 for in plane strain, because this is very long in the x3 direction. Epsilon 3, 3 is equal to 0. So sigma 2, 2 is equal to 0 as well, because this is a thin film. And then epsilon 3, 3 is 1 by E, sigma 3, 3 minus nu sigma 1, 1, sigma 2, 2 is 0, remember, and epsilon 3, 3 is 0 because of the plane strain condition, which means now I can find sigma 3, 3 in terms of sigma 1, 1, and then I can write the relationship between sigma 1, 1 and epsilon 1, 1 using this constitutive equation for epsilon 1, 1. In place of sigma 3, 3, I replace the value of sigma 3, 3 in terms of sigma 1, 1 from here to here, and this is what I will get. So epsilon 1, 1 is sigma 1, 1 by E prime, and that is the only component of stress that exists in in this part of the film. So everything is bonded. So when you pull it, only this part elongates, and strain energy is stored only in the debonded part. The debonded part, the strain energy, remember, is W. Remember, for a elastic material is sigma ij epsilon ij. In this case, it will be just sigma half sigma 1 1 epsilon 1 1, because uh, sigma 2 2 is 0, sigma 3 3 is not 0, but epsilon 3 3 is 0. So only term that we are left with is this, and the relation between sigma 1 1 and epsilon 1 1 is given here. So we'll plug this back into this. This is the energy per unit volume. We'll have to integrate this over the volume being the volume of this debonded part, to get the total strain energy in the system. So that's what we are going to do. So first we are going to find U um, times the volume. So this is, the volume is missing. So half sigma 1 1 epsilon 1 1 is this, times h times b times a, b being the breadth of the width of the of the film. H times b times a is the volume, and writing sigma 1 1 in terms of f. So sigma 1 1 is f divided by h into b. So using that fact, this is the total energy, strain energy, stored in the debonded part of the film. Now, uh, crack area is b times a. So del u del a, which is equal to g, will be f square by 2b square h e prime. You just uh, you just take a derivative with respect to b times a, and then using the fact that uh, g, g is equal to k square by e prime for a plane strain case, we get a k of this form. But uh, this step to this step, is uh, not really feasible, because the G is a combination of K1, K2, and K3, and we are not sure that this is a purely mode 1 problem, because the crack lies at the interface between a soft film and a hard substrate, and we do not know whether, in fact, it is not probably in a mode 1 situation. So what we find from here is not the real k at the tip of the crack. The G is real, of course, the G is correct, but from G, when we back out the k, we only get to the fact that the k will go as 1 by square root of h. The k will grow as 1 by square root of h. So you will have a higher and higher stress intensity factor at the tip, uh, as the thickness of the film decreases. But beyond that, this is not a mode 1k. This is some kind of averaged k, which is uh, maybe uh, a sum of k1 square plus k2 square. So this k square is what we are finding by multiplying g with e prime. We are not finding k1 and k2 separately. So that is an issue. We cannot directly split the k that we get from here into k1 and k2, unless we are sure that it's a pure mode 1 or a pure mode 2 problem. In this case, we are not sure. So the k that we find is probably k1 square plus k2 square root over. Okay, let's take a similar problem. In this problem, uh, what we have done is, we have taken a film, we have strained it uniaxially in the x1 direction. In the x1 direction, we have strained it first by a strain of epsilon naught, and then we have pasted it on this rigid substrate. It's again a thin film, so similar considerations about the stress, state of stress applies here as well. But here the question is, after we have pasted the film, after we have stretched the film by epsilon naught and then pasted it on the substrate, uh, what value of epsilon naught will it be able to tolerate? So how much can I stretch it before placing it on the substrate so that it does not debond from the edge? Okay, so when I paste it on the substrate, it tries to contract because I have stretched it. And this, while it tries to contract, it tries to peel off from the substrate. And what is the value of epsilon naught? What is the value of epsilon naught that will be that what is the maximum value of epsilon naught that will prevent the debonding from happening? We are also told that the critical energy release rate of this substrate is experimentally has been measured to be GC. So now again, we know the relationship between sigma 1 1 and, so we know that epsilon 1 1 is equal to sigma 1 1 by E prime from the previous problem. And in this case, epsilon 1 1 is epsilon naught that is given to us. So sigma 1 1 is E epsilon naught by 1 minus nu square. So this is this follows from the same considerations that we used in the previous problem. Because the film is small and it's debonded and so on. Now, with this stress, we can now find the energy. So the this stress now is this part of the film which has debonded. This part of the film which has debonded is actually stress free. The stretch that you had put gets relaxed as soon as this part gets debonded, but epsilon naught is still valid in the bonded part, right? So the to calculate the strain energy, we have to calculate first the strain energy density, which is half sigma 1 1 epsilon 1 1, which is equal to half E by 1 minus nu square epsilon naught square. This is the strain energy, and we have to multiply it by the volume, and the volume would now be B times H times the length of the undebonded part, which is L minus A. Okay, so this part is relaxed of this residual strain that was there in the film when it was pasted on the substrate. As soon as this debond forms, the strain relaxes here, but it does not relax in the undebonded part. So this is your strain energy, total strain energy, and then taking the derivative with respect to B times A will give you the G will give you the G. Now, the crack will start to, the debond will start to propagate catastrophically as soon as G equal to GC. So, as soon as this quantity is equal to GC, it's going to propagate, and therefore epsilon naught square equal to 2 GC, epsilon naught square that it can tolerate before it starts to propagate is 2 GC divided by E prime H, and therefore epsilon naught is root over of this. So this is your epsilon naught that you can give to this to the film so that it does not propagate, given that you have experimentally determined the value of GC at the film substrate interface. Okay, so the third problem that I'm going to do is called a double cantilever beam specimen. So the specimen is held here, and it has a crack that is pre-cut into it. In fact, this specimen is used for many fracture tests, and this is a mode 1 problem where the crack propagates in this direction. And in this situation, you have to calculate what is this is the, since this is a mode 1 problem, if we calculate the g in this case, we can find the k1 for this sample. Now when I apply a force p at this end of length a, then I can assume that this part is a cantilever and so is the lower part built in here. So this delta, so this delta will be split between the two. So delta by 2 will be equal to p a cube by 3 ei. I is 1/12 into uh, the thickness is b h cube. So this is what it is. So the total delta is going to be 2p a cube by 3 ei, which gives rise to, so this is 1/12, sorry. So this gives rise to 1/12 bh cube, and this will probably give rise to 8. This cancels, you get 4, so you get 8 here, and then you get 8p a cube by eph cube as delta. The crack area is again b times a, and then I can take the derivative of this to, I can now calculate the total energy. So the energy is half p times delta. So delta I know, p is what I have applied. So this is the energy. Take derivative with respect to b times a, and this is the g that you get. This is the g that you get after you take the derivative with respect to the area of the crack. Now, the assumption here is that these edges are such that the slope here is equal to 0 as well as the displacement. Both are 0, so this can be treated as a built-in edge. In reality, there may be some rotation here, in which case the effect of that rotation will also have to be taken into account in the strain energy. So with that assumption, this is the G that we get. And when this G equals GC, the crack will start to propagate. So if I just keep on increasing P slowly to see whether this crack propagates or not, the moment it starts to propagate, I can use this formula and find GC from there. You can also figure out if the crack growth is going to be stable or unstable in this particular example. Okay, so the last point that I want to make before before dealing with configurational forces is that GC is a parameter that governs when the crack is going to grow. So G equal to GC is a situation that we need to achieve in order for the crack to grow. So one way to stop the crack from growing is to make GC GC higher for a material. And then many techniques have been devised in order to increase the intrinsic fracture toughness, the critical fracture toughness of a material. So uh, here are some ways of toughness control. For example, if we have very very tough particles dispersed inside the material at a microscopic level, if we have inclusions in the material, then a propagating crack will have cannot go through these inclusions, and then will have to meander. We'll have to go around the inclusions. So in a mode 1 crack will therefore necessarily have to go into a circuitous path in order to propagate. So the more crack length you have, the more crack area you need to generate in order to propagate the crack, the more will be your GC. So this is one way of increasing your GC. The other way of increasing your GC is known as transformation toughening. What is done in this case is instead of using just inert particles, you have particles in the matrix which undergo stress-induced phase transformations. And these stress-induced phase transformations are such that the transform phase will have slightly higher volume than the untransformed phase. So when a crack propagates, there's high tensile stresses at the tip of the crack, and these tensile stresses will lead to the transformation of these particles from one phase to another, and the transform phase will have a slightly higher volume, and these transformed materials, slightly higher volume materials, are going to impose a compressive stress which will tend to close the crack, thereby making it a little more difficult for it to propagate through, because as it propagates there are particles transforming and increasing in volume and imposing a compressive stress on the path of the crack. So this is another way of increasing the toughness, increasing the toughness of ceramics, for example, which are very brittle materials, very hard but very brittle materials. And zirconia is one particle that is routinely used. To zirconia toughened ceramics are routinely used in order to increase their toughness. The other way to increase toughness is to dissipate the energy. Remember, if I allow a single crack to grow, if I allow a single crack to grow unhindered, then it's going to fracture the specimen. But a crack will, so I need to form new crack surfaces for a crack to grow. Now imagine what will happen if I don't allow a single crack to form the new crack surfaces, but I distribute the crack surfaces that are formed. So instead of propagating this main crack, I have some mechanism by which I form these micro cracks, many of them. So each of them add to the delta A, and each of them consume an energy Gc times delta A, and thereby reduce the overall energy of the system but protect the main crack from growing. In that way, by distributing the crack growth, by causing the growth of micro cracks, I can toughen the system in the sense that I prevent this main crack from growing, because it is dissipating its energy in forming many small cracks rather than concentrating all the energy on growing itself. The same thing can be done if I, instead of cracks, I form micro voids all around the main crack. These micro voids will take energy to form, and this energy accounts for the GC. This energy accounts for the GC and increases your GC, so that you need a higher G to propagate the main crack. So these are usual methods of toughness control, which does things at the level of the material, of the grain, of the material's microstructure, in order to increase its intrinsic toughness. There are other methods for this. I'm not going through all of them. One of them is to have fibers. So these fibers, if there are many of them all around, when a crack propagates, it has these fibers bridging the two crack surfaces, and thereby these crack surfaces are not exactly traction free surfaces, but because of these fibers, if you remove the fibers and draw the free body diagram, you have cracks with closing forces applied on them due to the extension of these fibers. As the crack opens, these fibers extend and they apply a closing force on the crack faces, which makes it a little difficult for the crack to open up, and thereby increases the GC. So increasing GC is an idea that emanates from Griffith's theory. These ideas about increasing GC of the material emanates from Griffith's theory, and very many such ideas are used routinely in the materials industry in order to create tougher and tougher materials. So we will stop for this week here, and in the next week we will try to generalize the scope of this energy release rate in such a way that it remains applicable to not only linear elastic materials but also materials uh, which are also a wider class of materials. Okay, so let's stop here for this week.